Today we are going to wrap up Unit 2 with Lesson 13. That's called Two Graphs for Each Relationship. And we're going to be looking at pretty much one situation for this entire activity today. And it's about a race. And we're going to be comparing the two different relationships. We're going to look at two different lines on a graph and what that means, the two different equations, and just a lot of compare and contrast between the two. So here's the situation. It says, in Mrs. Beckham's class, Emil found out that his walking rate is 2.5 meters per second. When he gets home from school, he times his little brother Henry as he walks 10 meters. He figures out that Henry's walking rate is 1 meter per second. Henry challenges Emil to a walking race. Because Emil's walking rate is faster, Emil gives Henry a 45-meter head start. Emil knows his brother would enjoy winning the race, but he does not want to make the race so short that it's obvious his brother will win. So Emil walks 2.5 meters every 1 second. So Emil's speed, his unit rate, is given to us. And Henry walks 1 meter every second. So we have Henry's unit rate, Henry's speed. So that would also give us the constant of proportionality in that relationship. There is one added thing though. So it says Henry has a 45-meter head start. So he is not starting at the same start point as his brother Emil. So let's fill in that chart. Let's look first at Henry, and this is where we've got some differences in what this table is going to look like. So for Henry, at 0 seconds time, we're going to be recording the distance in meters at each of these time intervals. So at 0 seconds, it would seem like Henry would be at 0 meters. But remember, he has a head start. So we're going to begin Henry with 45 meters. Then every second that passes, Henry's going to travel 1 meter. That's his speed, 1 meter every second. So in 1 second's time, he would have gone 1 meter further. So he would be at 46 meters, not 45. But he's traveling in 5-second intervals. So every one of these seconds, he's going to travel another meter. So 45 is going to become 50 when we get to that point. Then another 5 seconds pass, and he's gone another 5 meters. And that's going to continue for the entire table. Oops. All the way up to 90 meters. So that would be the furthest distance, at least that we're going to represent here in the table. We don't necessarily know how far they raced or where they ended, but we'll talk about that a little bit later. Now let's look at Emil. So Emil also has a speed, a unit rate of 25 meters every 1 second, every second, but he is starting at the starting line. Remember, Henry started 45 meters ahead of him. So at 0 seconds time, Emil is going to be at 0 meters. Then his constant of proportionality is 2.5 meters. So we're going to take each of these seconds times our constant of proportionality, 2.5, to get his distance. So the first distance after 5 seconds is 12.5 meters, then 25, then 37.5. Each of these I'm finding by multiplying the time times Emil's speed of 2.5, that constant of proportionality. So if we continue, in 20 seconds time, he would have gone 50 meters, then 62.5, 75, 87.5, 100, and 112.5. Okay, so that answers the first part. That filled in the table and was with all the information we were given here in the situation. Now we're going to have to look at some of this data and make some comparisons. So for part B, it says, how long should the race be so that Henry will win in a close race? Now, winning a race would be going the furthest distance. And if we look at this table, we can see Henry's change in distance and Emil's, and what I'm looking for is a comparison between them. Here, Henry's far ahead of Emil, but slowly Emil's going to be catching up to him. Here, their numbers are much closer, their distance from the starting line, because Emil's traveling faster. So we get closer, and then here is a really, really, really important point. At 30 seconds time, they have the same distance. Now think about what that would mean in a race. So in 30 seconds time, both boys are the same distance from the starting line, 75 meters away. So they're side by side, neck and neck would be the way to describe that race. So if we continue and look 5 seconds later, Henry is 80 meters from the starting line and Emil is 87.5 meters away. So here, Emil has passed his little brother. He's gone farther from the finish line at this time point, this timestamp, and he is now winning the race for the rest of the race, and that's going to continue because he's traveling faster. So if we go back to the question that's asking how long should the race be so that Henry will win in a close race? So we don't want a time after 30 seconds because then Henry is no longer winning. He's falling behind his brother. If we look at exactly 30 seconds, they're side by side. That means that Henry is not winning, they are tied. So we would want a time for the race to be less than 30 seconds. You could say maybe between 25 and 30 seconds would be a good time length for the race so that Henry still wins and it's a close race between the two boys. Okay, now we're going to be putting this on a graph. And it says, it tells us the intervals. It says use 5 for the x interval and 10 for the y interval, which means each of these markings is going to be 5 along, remember this is the x-axis here, so 15, 20, 30, all the way up. And it says use an interval of 10 for the y-axis. So on the y-axis, we're going to be going up by tens, 10, 20, 30, 40, up to 100. Now, we're going to graph our lines. So we have back in our table ordered pairs. For Henry, we have the time and Henry's distance. The time is the x-axis, the distance is the y-axis. And then we can also compare that time to Emil and have an ordered pair there. So our first point here for Henry is going to be 0 and 45. 0 on the x, 45 on the y. For Emil, it's going to be 0, 0. So if we go back to that, if we keep the same colors, Emil's going to be starting at 0, 0. Henry is going to be at 0, 45. 45 meters from that starting line. And then they're both traveling at constant rates, at constant speeds. Remember, Henry was 1 meter every second, and Emil was 2.5 meters every second. So we can use that to plot our line. We could put all of the points that we have there in the table. Truthfully, though, we really only need one other point because we're going to be connecting it to the starting point for the race out to a point here. So I do know that at 30 seconds time, they both were the same distance away from the starting line. That was 75 meters. So if I go at 30 seconds up to 75 and plot a point, that would be right here. And really, it's going to be blue and green because they share that same location. Now I need to connect their starting point. Since they're traveling at a constant speed, it'll be a nice straight line to that location. And for Henry, we'll do the same, but he's starting right there. All right. Now, I could certainly put other points along here, but I do not need to. This line represents all those data points in the table and any others that we would want to know. Okay, and I definitely know where they're starting and where they're both going to cross, where they're going to meet. So let's take a look now, and let's see, let me label these lines just so we don't get them confused. So Emil was green and blue was Henry. Now we're on to the questions that you see here. So it says, how could you use the graph to help determine how long the race should be? That's what we've already talked about. We said the race should be between 25 and 30 seconds. But we were looking at a table when we decided that. Here on the graph, you can see that intersecting point of the two lines is that point at 30 seconds when they were the same distance away from the starting point. Before this point is where Emil is behind Henry. Henry is a greater distance if we look at the y-axis here. At this point, Henry has gone a greater distance from the start than Emil has. So if we looked, say, at 25, if we looked at 25 seconds, here it would intersect with Emil and here with Henry. That would put them at about, and this might not be exact, but for Emil, he's about 60 meters from the starting point, and Henry is about 70 meters from the starting point. So he's still ahead of him by about 10 meters in the race, as Emil is starting to catch up to where they get to the same distance side by side here. Lastly, let's look at part F, write an equation representing the relationship between time and distance. Explain what each number and variable means. So let's go ahead and use X and Y. Remember, we have a formula for a proportional relationship. We want to represent an equation that's Y equals K times X, the constant of proportionality times X. And since we have our axis marked with X and Y, let's just use that. So let's look at Emil first. So Emil traveled 2.5 meters every second and started here at the origin. That's a proportional relationship. So that, and let's do that in green, that should fit what we want to see for a proportional relationship. So we would get the y, the distance, by multiplying Emil's speed, his constant of proportionality, by x, and that would be the time in seconds. That should work for any of those points that we had in the table or here on the graph. Now for Henry, this is a little bit different story. I think in first opinion, you might look at this graph or that table and say, yeah, Henry is a proportional relationship as well. But it's not. Remember, a proportional relationship is shown on a graph with a straight line, but that straight line must be able to connect to the origin of the graph, 0, 0. In this case, it doesn't. It's intersecting the y-axis here at 45 meters. It's not proportional. And this will make sense as we talk about it. So if we were trying to show y equals K times X for Henry, we would use Henry's speed, his constant of proportionality, or his what we would call the constant of proportionality, his speed, which is 1 meter per second times the seconds times the time. If that were the case, if he was running for 5 seconds in this equation, 5 times 1 equals 5. All of our x and y values are going to be the same. If he's running for 10 seconds, 10 times 1 equals 10. That would be the same as well. But we know from the table that's not true. Whatever the time was is not the same amount as the distance in meters. And that was because Henry had a head start. He started 45 meters ahead of where Emil was starting the race. So we need to increase all of these quantities by 45 meters to get those correct distances that we had in the previous table. Now, this is not the equation that we would use to represent a proportional relationship, and we can see proof of that here in the graph because it's not going to the origin. We could see that in the table because all of the values for Henry here are not increasing by the same constant of proportionality because he started at this 45 meters. So let's continue to answer a few questions about this. If we look at the next part, which is still talking about the same situation here, it asks, how far does Emil walk in 20 seconds? So I'm looking back at the table from what we just did. And at 20 seconds time, Emil has walked 50 meters. After 20 seconds, how far apart are the brothers? How is the distance represented in the table and on the graph? So I could look at the table at 20 seconds time. We said Emil was at 50 meters and his brother Henry is at 65 meters. So how far apart are the brothers would be the difference between their two distances. They're 15 meters apart. And because Henry is a greater distance, that means Henry is ahead of Emil by 15 meters. So we would just subtract to show that they are 15 meters apart, or Henry is 15 meters ahead. We could see that in the table too, or in the graph also, but I think the table is a good way to represent that. The question asks, is the point 2670 on either graph? Well, we could look at the graph and see that at 26 seconds, that there is no distance that would be at that point. So the answer to that would be no. And then the last question, when will Emil overtake Henry, overtake or pass him in this race? We've already clarified that happens, they are neck and neck, side by side at 30 seconds. So we would say after 30 seconds. Now we could say 31 seconds or more, but technically, even a part of a second is going to allow Emil to pass his brother Henry. So 30.5 seconds would also be a possibility. So just saying after 30 seconds is a safer way to include all possibilities here. All right, and last, let's look at the conclusion to this. So the first question says, how can you determine which of two lines will be steeper from a table? Now, this goes back to what we just looked at. Remember a lesson or two ago, we talked about a steeper line and what that represents. It represents a greater constant of proportionality. There's more change happening in the amount of time that's occurring. So in this case, in the table, we would be looking at how can we determine which of the two lines will be steeper. We'd be looking at which relationship has a greater constant of proportionality. Remember, Emil was traveling at a speed of 2.5 meters per second, and Henry was 1 meter per second. So greater speed, greater constant of proportionality, so that's going to be the steeper line. We could also look at all the distances that we're calculating and see that the change between each of those rows in the table is greater. So if we look at Emil's, every 5 seconds, he was increasing 12.5 meters, whereas Henry was only increasing 5 meters every 5 seconds. There's a, a slower change between those amounts. Then it talks about equation, same idea. So in an equation, how can we determine which of two lines will be steeper? It's going to be the one with the greater constant of proportionality. At what point do Emil and Henry's graphs cross the y-axis? Where do they intersect or cross the y-axis? So if we go back to our graph, they were these 2 points. It's basically the ordered pair that has 0 seconds. That was for Emil. And at 0:45, that was for Henry. That would be where they're crossing the y-axis when the x value is 0, when there's no change on the x-axis. Those points represent, that's the starting point of the race, something we've already talked about. All right, and how can these, so just clarify, what information do these points represent in terms of the race? That's where they both started. How far from the starting point was each racer at the start of the race? 0 seconds had passed, the race hadn't started. That was their distances from the starting line. How can these points be found in a table? Well, it was the first row of our table. At 0 seconds time, what were both of their distances? Okay, and how could those points represent in an equation? It's when x equals 0. So when we insert 0 for x, what would that represent? Okay, that was an overview of this activity, of some comparisons, but it was also bringing together a lot of the same ideas that we have been working on in Unit 2 with proportional relationships. So I hope at this point that you're very comfortable with what these graphs of proportional relationships should look like. Remember, they should have a straight line and they should be able to connect to the origin. We're also talking about the equations and what form that equation must fit into to be a proportional relationship. We need to see that constant of proportionality, that k value there, and have nothing else impacting that relationship like we did here with Henry. Henry was given a head start, an extra distance, which created a relationship that wasn't proportional. All right. Tomorrow, we're going to spend some time reviewing for your quiz, which will finish Unit 2 and get us ready for Unit 3. So if you have questions, please jump on Zoom, ask for help, go back and take a look at some of the activities we've done for Unit 2 so you can practice and study for what you'll see on the quiz. Have a good day.